And today we attack Newton's method and learn this. Newton's method is a method of finding zeros of functions, which you've already done several different ways. You've done it by factoring. You've done it in rational functions where you set your numerator equal to 0. If it was a quadratic, you could use the quadratic formula if it didn't factor. You've done completing the square to find zeros. And we did bisection method earlier this year, which was kind of a pain in terms of how to do it and redo it and redo it and redo it to get it exact. But all those methods let us find something a little bit different. If I can't find it one way, then I can find it one of the other methods. So this is another one. It involves calculus. It is an iterative process, just like the bisection method was, but it takes fewer iterations to get your answer much more exact. It is named after Sir Isaac Newton, so let's jump in and see what we can learn. I thought before we got started, we might look at a couple of quotes, things that you didn't know or you might relate to from Sir Isaac Newton. The first one's a quote that reflects a good practice for learning calculus. I keep the subject of my inquiry constantly before me and wait till the first dawning opens gradually, by little and little, into a full and clear light. If you've gotten frustrated with any of the material in calculus, it didn't just dawn on you and you didn't just immediately understand it, know that you're in good company. It didn't happen immediately for Sir Isaac Newton either. He kept thinking about it, and there would be little bits of things that he would understand, and then a little bit more and a little bit more. So that's the way that you've got to approach learning calculus. Little bits and pieces at a time. Get a hold of something, make sure you understand it, and it will open something else for you. Okay, don't get frustrated. All right, the next one, it's a quote that reflects a side of Newton you may not have known. The most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent being. All variety of created objects which represent order and life in the universe could happen only by the willful reasoning of its creator, whom I call the Lord God. I love where it says willful reasoning, and I underline that for a purpose. This implies that it wasn't an accident. God's voice may have echoed as if it were a big bang, but it wasn't just a big bang and things happened. It was a bang of his voice that echoed a thought that had gone into it, a willful reasoning. He wanted it to happen this way. He thought about it ahead of time. He reasoned it out, what would be the best thing for us here on the earth. Granted, we live in a fallen world. People have gone against what God wanted, and yet still he knew that would happen. And he planned for Jesus to come as, again, a willful reasoning for us to be able to make our way back to him. So nothing there that could by any means be just happening or I lost the word, but Darwin's theory. It just couldn't just happen, and things just couldn't evolve. It was willful reasoning. And then, in the absence of any other proof, the thumb alone would convince me of God's existence. None of us, if we were to create something, would think about all the things that thumb can do, how it balances things when you grab. If you just lift things up from the bottom, the thumb balances on one side. Think about trying to do things without your thumb and how difficult that would be. It's very necessary for us to be able to accomplish the things that we do. And so just another way that God thought of us and designed us to be able to honor him. All right, so Newton's method for approximating zeros. What we're going to do on this is guess a first approximation to a solution of the equation f of x equals 0. Okay, a graph may help, or we could use the intermediate value theorem, and that's what we're going to do on our next one, on our example in a minute. Okay, and then you use that first approximation to get a second, the second approximation gets a third, and so on, using this formula right here. X sub n plus 1 equals x sub n minus f at x sub n over f prime. Okay, so you're going to figure out an x value, and you're going to plug it in here. Then you're going to plug it into the function, and then you're going to plug it into the derivative of the function. Okay? All right, now then do notice that, with that f prime on the bottom, that if f prime of x equals 0, Newton's method is not going to work. So again, we've got some limitations, but it's really a nice, handy method. Okay, so what I want to do is to use 4 iterations of Newton's method in order to solve x cubed plus 3x plus 1. Now, if I think about my intermediate value theorem on this, and I plug in 0, okay, we're going to say here that, grab a different pen, f of x equals x cubed plus 3x plus 1. And so if I plug in 0, then that's going to give me 1. So that's a positive value. Now, if I go further to the right, with all the signs being positive, everything's going to continue to be positive. So let's go 1 to the left and see what we can find out. F at negative 1, that's going to be negative 1 and minus 3 and plus 1. So that looks like a negative 3, and that works great because if I have the point negative 1, negative 3, and then the point 0, 1, I know that there has to be a place in between there because this is a polynomial, so it's a continuous function. Continuous function, I've got to have a 0 in between there since I went straight from negative 3 to 1 on my y values. So intermediate value theorem helps us out there. And so let's guess something. I'm going to guess, I don't know, let's say negative 0.5. Who knows? Something between 0 and negative 1. So let's say that my first graph, or my first guess at x is going to be a negative 0.5. Okay, now I'm going to pull up the calculator and let's see if we can get this to work. Okay, hopefully this is still showing up for you. Okay. So I put the original function in at x cubed plus 3x plus 1, and I put 3x squared plus 3 into the y2 value. Okay. So, I could go back to my home screen, second quit, okay, and plug these in. You could use your table, but your home screen's a little bit nicer. Let's take our 0.5, let me go back, negative 0.5, and let's plug that in place of x. So I want to store that in my x position. Okay, so 0.5 stores in x, enter. Okay, and then what I want to do is x minus, and your bars, y bars, function is y1 of x divided by y2 of x, so bars again, y bars, function, y2 of x. Okay. Well, that gives me negative 0.3 repeating, which is a negative 1/3. So if my original value over here, x1 was negative 0.5, then my x2 is negative 1/3, negative 0.3 repeating. Okay, so then grab your calculator again. Let's pull it out. And this time what I want to do is I want to take that value and I want to store it. Store that answer into x. Enter. And it tells you now your x value is that. So again, you want to do the same thing. X minus. Okay, or go up and plug your, if yours will let you go up and snag that and do that. Okay, there's your next one, negative 0.322. So that's going to be my x3 one. All right, and let's do it one more time. Pull that calculator out. Okay, and I'm going to store this into x again. Store x. Enter. I'm going to go back up, hopefully, and see if it will let me do this without having to do that. Ah, there we go. Okay, so negative 0.322185. And I know it said go 4, but let's go one more just to see how close we are. Because as these decimal places get to where more and more of them are repeating like this, then you know you're getting more and more accurate. So let's do it one more time since that wasn't too terribly much trouble. Store it into X, enter, go back up, enter, enter. And you get negative 0.322185 again, don't you? All right, and so therefore you know that you are accurate to several decimal places there, and so you're in good shape. You've got the right answer, okay? So that's not really a problem at all, okay? Okay, but I want us to be creative on this and figure out how we could use our calculators to be even more helpful, just to make it one step simpler on this, okay? On this right here, if I store x as, oops, let me do clear, and do negative 0.5 and store it as x, going back to what we did earlier, okay, it's back to that. Now then, here's this really cool thing that you can do. You start up the same, x minus y bars. Yes, I know I'm repeating myself and it's easier not to do this, but of x divided by bars, y bars of x. But if I will do store x right there, then that answer is automatically stored in x. And all that I have to do from there is just hit enter until I get the degree of accuracy that I'm looking for. And so that makes it really nice. I don't have to have any kind of special program or anything like that. I fixed it and I can hit enter 4 or 5 times and do as many iterations as they want me to do. Okay, Newton's method is on your AP exam. It's not on there a ton, but it is on there, so be sure that you know what you're doing with that. And that's it for now, and hope you have a great afternoon or morning, whichever it is that you're listening to this. Talk to you later. Bye.